Yeah, Rakesh sir, good evening. Rakesh, good evening.
Good evening, sir. Good evening.
Yeah, good evening, good evening. Yeah,
Good
happy
evening.
to see you once again.
Thank you, sir.
Yeah,
Thank you.
thank you very much for taking this session. Yeah, dear participants, so already Rakesh sir has taken a first session in the first day. So I'm very thankful to Rakesh. Once again with us, we are very happy. Yeah, you can start session, sir.
Yeah. Okay. So I hope everybody can see my screen, right?
Yeah, it is visible.
Yeah. Okay. All right. So this would be basically the theme of my talk. Natural language processing for threat intelligence. That was a topic I was asked to speak, but taking slight liberty, I have changed the focus of the talk. I'll start with NLP as per the topic, but I will slightly deviate to the work that I want to means where this NLP can be used. So as a case study, I will be presenting about IoT botnets and how NLP can be used to analyze this threat intelligence. So I think over the past 2 3 days, you must have everybody must have uh, gone through different concepts related to cybersecurity threats and their mitigation mechanisms using with especially focus on machine learning. I guess that would be safe to assume that last 3 days would be intensively on those topics. So as we see, like in the at least in the past 2 years, the usage of the availability of number of tools, advanced tools that are doing this natural language processing has increased tremendously, right? All big major corporations have come up with their own generative models, right? So basically if everybody must be using in their teaching and other day-to-day activities, technical related. So everybody must be aware of this natural language processing, right? So let us say we have some tools like ChatGPT or DeepSeek or Gemini, like that we have Grok, right? We have different these generative AI models, right, which can perform lot of analytical tasks for us, right? So the same tools can also be used for threat intelligence, right? So that would be the main core of this particular talk, right? So even though everybody knows what is natural language processing, just for the continuity and just for the understanding of everyone, I'm starting with this simple definition of NLP, right? Basically this is a field of, means we have seen artificial a lot of AI tools, right? So NLP is also basically a part of artificial intelligence, and also a lot of domain expertise on linguistics is required, right? So it is a part of computational linguistics. The basic concern is now about how how humans or human languages can these machines learn, and what kind of interactions can be done from human to machine, right? So that's basically is the essence of NLP, right? So once machines can, if machines can understand how human, I mean human languages, then lot of this manual processing that we do can be completely mechanized, right? So that is a major completely automated, right? That is a major problem that we will be solving by deploying or by employing NLP, right? So basically, NLP goes beyond structure matching, right? Basically, structure matching means identifying the structure and meaning of words, sentences, texts, and conversations, and develops a deep understanding of the language, right? So basically, NLP is all around us. If you can see, this is a cartoon which is depicting how means how a dog interprets human language. For example, the dog's name is Ginger here, right? So the person is saying something, but what does the dog understand? If you see, the dog understands only the word ginger, blah 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 blah, ginger, blah 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 blah. So basically what it means is that the dog's cognition is only to recognize that word and accept that everything is everything is blah blah for the dog, right? So we want to remove that, and and we want to ensure that the machines basically can understand our natural languages, right? So how this can be leveraged for threat intelligence? What exactly do we mean by threat intelligence? So threat intelligence is basically all sources of information, including human sources, right? All these sources of data from different modes that can be means web pages, that can be some HTML files, that can be JSON records, that can be log records, system records, that can be PDF files, that can be audio files, that can be human intelligence or human inputs, right? All these different vectors of intelligence related to threats are given to a something like a black box that we are calling it as the NLP box, right? This all these records, if you have to manually understand, right? If you have to manually process, even if you have to process using machine, that like a computer, right, it becomes very difficult to generate something of meaningful intelligence, right? So but once we have something like a NLP processor, right, for example a generative AI machine, like you give all these records to your chat GPT, right, LLM, large language model, right? So this the model can basically integrate different modes of data and can generate sufficient intelligence. So for example, any security analyst that has used an LLM, for example, for processing, right, can generate normal, using normal language, can generate queries and can do or can understand or can like basically generate intelligence out of this huge amounts of data, right? So where can we apply NLP? We can apply NLP for threat intelligence analysis, that we have already detected, already said. Automated incident response, right? Most of the security systems like security operations operation center, consisting of security information and event management system, SIEM, that we call as security orchestration, automation and response, SOAR, security orchestration, automation and response, SOAR, SIEM, SOAR tools, right? When we have these tools, right, lot of alerts are generated. Most of these alerts are manually attended by security analysts or your security team, right? But that wastes lot of your significant energy on regular alerts, right? So that can be completely automated if you have something like natural language processing, right? So majority of the alerts can be automatically handled and only specialized alerts can be looked after by security operations center. So this basically lowers the amount of effort that a user has to put in to analyze these records. Also, right, one of the most other important thing is multilingual threat analysis can be done, right? So your information can be from multiple sources and in multiple languages, right? So if you have something like a LLM, right, what you can do is you can pass on all these records to this machine and it can analyze these varied or diverse information sources, right? So you can use NLP for phishing detection, right? Lot of malwares are generated or propagated through phishing emails, right? So sophisticated phishing detection is very important for you to prevent these malwares from spreading, right? So you can also use NLP for threat intelligence like phishing detection and log anomaly detection, right? So and detecting insider threats. Of all these are different various branches that you can use, or various domains that you can use NLP for generating different types of threat intelligence. Uh, so, for example, what is different and why having a tool like an NLP processor would, or like a large language model will help in this particular aspect of cybersecurity. If we just try to find answer, the major change that lies in is the variety of sources from which the data is being generated and the amount of data, that is main important, right? The amount of data. For example, log anomaly detection, right, is a simple task of analyzing log records and try to see if there is any kind of anomaly. For example, somebody, like for example, the current Typically, means it is quite odd that we are having this workshop at 7:30 to 9, right? So this is not usually considered as a means when you are this is slightly odd, right? So this is an anomaly, right? I mean, I do not mean in any other way, but this basically can be considered as an anomaly. For example, a user who is supposed to log in from his system in the office suddenly logs in from a remote location somewhere which is not which is very odd, right? So that we can consider it as an anomaly, right? So these type of anomalies can be easily detected, right? But what is a major task that this NLP is bringing in, or for that matter any kind of model that is machine learning model that is bringing in, is the large amount of data that can be analyzed, right, in a very short span of time, accurately as possible, right? So that is a major challenge. All these different types of domains can be benefited by the use of NLP, right? So what is the goal? The goal is mainly to extract indicators of compromise, right? IOCs. We call them as IOCs, indicators of compromise. Map tactics, techniques, and procedures to accelerate analysis, right? That is our goal. And as I've said, why we are using this now? Because of the exploding unstructured security text, especially alerts, tickets, blogs, dark web, etc. Right? So where can this NLP fit? NLP can fit in your SOC, Security Operations Center, your SIEM, Security Information and Event Management System, and your Security Orchestration, Automation and Response. Right? So the applicability of NLP is in multiple components of your security system. What exactly is threat intelligence and how do we arrive at these threat intelligence, right? What are the major sources of threat intelligence, right? For example, if you take like if you correlate with the security agencies, what they do, they collect a lot of security information, right? Security agencies, I mean, like raw research and analysis wing, right? They have lot of various sources from which they gather information. Similarly, in the cyber world, you can gather information from multiple sources. Like, for example, OSINT, we call it as open source intelligence. Vendor feeds, different kinds of vendors. For example, Virus Total, they keep generating these malware signatures and malware samples that is open, and you can actually download. Means you can actually get that data from those different platforms. Can you? I think there is some crosstalk. Can you please mute?
Please, dear participants, please mute. Please on your mute. Please, dear participants.
என்னென்ன பண்ணணும்னு சொல்லிட்டு அப்பப்போ
Excuse me, please.
மோகன் சார் போன் பண்ணிட்டு இருக்காங்க. அதான் இம்பார்ட்டன்ட்னா.
Yeah, proceed, sir. Muted.
Yeah, so can you see my screen?
Yeah.
Okay.
Yeah, it is visible.
Thank you, sir.
Yeah.
Thank you, sir. Thank you. Yeah, so like how we means how they means we have several open source platforms from which we can gather intelligence. We can also gather intelligence from vendor feeds. We can gather intelligence from social media. We can gather intelligence from dark web. We can gather intelligence from incident reports, right? All these are various sources of intelligence, right? How is this data arriving with us, right? The data is arriving in different formats, like for example, structured formats, that we call it as STIX, right? Structured threat information expression, right? And TAXI, trusted automated exchange of indicator information, right? So you get the data in structured data, you get data in semi-structured data like CSV files, you get data in unstructured like blogs, posts, PDFs. It can also be audio files, audio recordings, it can be images, right? All these are different forms in which data is received, right? These two things are very important. STIX, for example, structured threat information expression, is a data format that is used to exchange especially threat intelligence, right? JSON objects, it is represented as a JSON file that describes threats like indicators, malware, actors, TTPs, relationships, reports. All this is presented in the form of a JSON file. And you have something called as a taxi server, right? Taxi server is nothing but a transport or an API, means application programming interface. So these two are used, or these two work together to move or to exchange threat intelligence from one place to another place, right? So this is structured way, right? Structured, we already have certain tools and certain mechanisms to analyze this, right? But what about unstructured data or semi-structured data, right? How can we analyze that, right? So the threat in means major task is to first collect data, normalization, enrich this data, analysis, and then disseminate, right? So what basically we are doing is information is shared, information sharing platforms via which companies and providers exchange information. We are actually means different sources like code repositories which provide information on the exploit code, news articles, IOC means incidents of indicators of compromise from different blogs, social media, right? And other agencies that that publish intelligence, threat intelligence basically, right? When you have all these things put together, you need to analyze these varied sources of data, multimodal sources of data, right? So what are the basic steps that while applying NLP for threat intelligence? First thing, that as I've said, text acquisition and normalization, right? Then you have something like word tokenization. You do segmentation, lemmatization, right? So basically mapping these words to some meaningful intelligence using different techniques, right? Then identifying stop words, these are all NLP techniques, right? Once you have that, then you are trying to do named entity recognition, like for example, what, from where, how, right? Dependency parsing, what did, what to whom, right? Who is affected, how is it affected, what is the IP address, whether IPv4, IPv6, right? All these are entity recognition, trying to identify the entity. Then document and language detection, if there are, so there might be multiple languages that are means that are applied to this threat intelligence platform. So we are trying to integrate all this into a common platform. So these are the core components, NLP components that are necessary for you to work on threat intelligence, right? Like NER, named entity recognition, like IPs, domains, file hashes, malware families, actor names, etc. Right? Threat actors, basically, right? Then relation extraction. So means extracting the relation from the data that you received, like for example, malware X exploits this common vulnerability enumeration Y. Actor Z targets sector S, right? Like that. This is relationship extraction. Once you have this, once you extracted this relationship, then classification that involves source, credibility, topic, priority, severity, etc. Right? So you can classify into multiple clusters, right? Topic modeling and clustering, denoise and group similar types of intelligence, right? Summarization. So basically, analysts ready digest from long reports, right? So means typically like summarizing the entire intelligence into actionable points, right? That is most important challenge that security operation centers are currently facing. So how text actually becomes vector? You use several different types of NLP techniques like bag of words, right? TF, IDF, term frequency, inverse document frequency. These are techniques, right? Word embeddings, contextual embeddings, entity linking. Like for example, this APT 28 fancy bear suffocacy. This is a Russian threat actor, right? That you can identify. Means once you have the intelligence to understand this, then you can basically identify the entity and map the entity to the threat intelligence source. So what kind of information are we extracting for identifying the IOCs, indicators of compromise? Basically, indicators of compromise means what? Like for example, there is an unauthorized attempt and you have seen that the unauthorized attempt was successful, right? That basically is recorded as a log record, right? So once you have something like that, then you can easily identify that this is an indicator of compromise, right? Then you have threats, techniques and processes, right? TTP. Basically applying the NLP pipeline, we can extract information from this like IOC patterns, TTP mapping. For example, extract the verbs, objects and align it to these platforms, Mitre attack platform, right? Common vulnerability enumeration platform. And then you can rate them using some kind of confidence scoring mechanisms like combining regular expressions with machine learning with context, right? So then applying all this, you can develop a confidence score for that, right? Once you have these two, then you can normalize and enrich the data, right? Using different types of tools like WHOIS, passive DNS, virus total like scores, and common vulnerability enumeration and national vulnerability database links, right? So you are enriching the existing data by supplementing it or augmenting this data with multiple sources, other sources. So here I would this is like brief of how NLP can be applied to threat intelligence or cybersecurity in general, right? So the major change here, the cybersecurity has come across is the explosion of data. The explosion of data. How we have generated or how we are getting huge amounts of data that manual processing cannot keep up with the types of threat intelligence that is being generated. So in my earlier talk, I emphasized on the major change that has happened is with the advent of IoT, right? Once you have this IoT devices connecting to the internet, the huge amounts of attack surface that has increased. So that has given rise to multiple types of different types of attacks that are happening. So the threat intelligence that is generated is huge, right? So to analyze this large amounts of intelligence, we cannot do it manually, so we need some kind of other technique to process this intelligence. So my next my way of validating this point is through botnets. What I want to show is that how we have used or how we have employed these techniques, especially machine learning and language techniques, NLP techniques, to identify and generate threat intelligence, basically intelligence that is only specific to botnets. So I am going to show you as a case study how we can apply these NLP techniques to generate intelligence and simplify the processing of data, right? So before we move on, I will just briefly give you introduction to the botnets, means how these botnets work, and I will tell you two case studies where we have applied these techniques, right, to summarize and speed up the process of detection, right? I guess everybody knows what exactly is a botnet, but for simplicity, a botnet basically is a collection of compromised devices and controlled remotely, right? So how does it work? You have a command and control center, and these bots receive commands from this command and control center, and they process these commands using they process these commands locally and perform the actions that are being instructed to, right? So why does it matter? They are used for distributed denial of service attacks, data theft, spam campaigns, and cryptojacking, right? All these are possible using botnets, right? How to identify them? How to identify them? If you have to identify them using statistically or using anomalous behavior, it becomes very difficult, because the amount of data that these devices are generating is very huge. So here something like an NLP module can simplify this process for you. They can detect the underlying spam campaigns. They can also detect underlying cryptojacking attempts. Like cryptojacking means basically hijacking of these devices for performing crypto operations like mining, crypto mining, right? Bitcoin mining, right? Or hijacking of processor capability, right? Processing capacity or computing capability, right? All this we call it as cryptojacking, right? So that is why it is important to automate these processes. So the essential components of a botnet basically include bot master, the attacker who controls the botnet, the command and control center, the infrastructure that is used to command the bots, and bots means the main components, the compromised devices performing malicious activities, a propagation mechanism, right? The way the malware spreads, for example, either through some kind of exploit or through some kind of credential stuffing, that is like brute force or stealing credentials, right? Or trying out all possible dictionary attack, for example, right? Once these things are there, then the final action takes place, such as launching of distributed denial of service attacks or stealing of data, right? So these are the critical components of a botnet. You have a bot master, you have a command and control center, you have bots, you have attack mechanism, you have propagation mechanism, right? So the bot master is mainly involved with operational control and resource management. The command and control center is mainly relevant to command delivery and communication protocols. Bots are the those end points that carry out your malicious activity, right? The resources are utilized from these bots, and finally the attack mechanism, that is either distributed denial of service attacks and data exfiltration, means stealing of data. What are the possible consequences of botnets? As we all know, distributed denial of service, right? Followed by data breaches and credential theft, that is stealing of sensitive user data, and spam and phishing campaigns, right? Sending fraudulent emails to victims, etc. Right? Cryptojacking, unauthorized use of IoT devices for mining cryptocurrency, right? Followed by cyber espionage and warfare. So these like state-sponsored cyber attacks, leveraging botnets, right? So these are all possible consequences of botnets. So, like just recollecting why this has significantly affected the IoT ecosystem, right? The major reasons being weak security policies. I discussed this in my earlier talk as well. That is, many IoT devices are shipped with default credentials, open ports, minimal authentication mechanisms, making them easy target for attackers. Then we also they also suffer from lack of firmware updates and security measures, right? Minimal security measures and no frequent update of firmware with security patches, right? So and you cannot install a typical firewall or antivirus software on that small IoT device, right? That's why they are very easily they can be easily targeted, right? And massive deployment scale, large number of devices can form network quickly, and they expose a lot of vulnerabilities for the outside world, right? So even through a few compromised devices, one can form a powerful botnet for different types of cyber attacks. And persistent internet connectivity, that is these devices are constantly online and they are constantly sending data, right? So that basically is kind of a gold mine for attackers. So how IoT botnets basically differ from traditional botnets is, traditional botnets use PCs, servers, smartphones, etc. IoT botnets use IoT devices like CCTVs, routers, DVRs, right? Video recorders. Now, infection method is through malware, phishing, and exploits. The infection mechanism in IoT botnets is default credentials, weak passwords, etc. The control model is centralized, peer-to-peer, and the IoT botnets, the model is often decentralized and hard to track, right? So if you can observe, even this task can be automated, right? By trying to find hidden patterns in the data that is being generated, right? The impact is this DDoS, spam, data theft, etc. The impact of IoT botnets is large-scale distributed denial of service, espionage, and cryptojacking, right? So what is the key takeaway that we can take from this is IoT botnets are more dangerous than traditional botnets because they exploit a vast number of insecure devices, making them very hard to detect and mitigate. So leading to a massive scale attacks with severe consequences. So what are the different malwares? So what are the different malwares that can create a botnet? We have Mirai, for example, the most different malware families exploit IoT vulnerabilities to create cyber attacks. Like for example, Mirai. Attack method scans for IoT devices with default credentials used in massive distributed denial of service attacks. For example, 2006 DIN attack. We have similarly Mozi, Gavgate, Tori, Hajime, right? These are all malwares whose aim is to perform a distributed denial of service. So they use peer-to-peer botnet spread via vulnerabilities. Hard to dismantle due to decentralized control. So you do not know which portion is managed by which command and control center. So it is very hard to dismantle. Even if you fix some parts, you do not know how many such command and control centers exist, right? Because of its distributed nature. So GAFGIT, also called as Bashlight, uses multiple exploits to infect devices, commonly used to attack gaming servers. Similarly, you have Tori that uses stealthy malware with advanced persistence, and it remains undetected for long periods because it uses different persistent mechanisms, advanced persistent mechanism. So Hajime, for example, it is self-propagating and its features are not known. There is a like understanding that possibly it can be a white hat botnet that is securing devices, right? The major point that I'm trying to make is IoT botnets exploit weak credentials, outdated firmware, and security flaws with stronger security. So there is a need for stronger security measures. So let us look at this specific botnet, Mirai, right? And then I will tell you what exactly how the solution has been designed using different types of machine learning and NLP techniques, right? So, for example, this Mirai botnet operates in 5 key stages. Mainly, the first stage is recon, that is reconnaissance, right? Recon basically happens before any type of attack, right? So, because let us say thief is trying to rob a home, right? He also does some kind of reconnaissance, like whether the owners are there. If they are not there, what is the time duration that they will not be there? So all those weak points are identified only through reconnaissance, right? So even Mirai does reconnaissance. What it does is scans IP ranges to find IoT devices with open ports and weak credentials. They are hard to detect due to minimal traces in public datasets. Exploitation, what does it exploit? Uses default usernames and passwords to gain control over devices, leveraging weak authentication mechanisms. And how is this command and control center established? Command and control center is established through a central command and control server, right? So, and it uses HTTP or HTTPS to send and receive commands. If it's using HTTPS, it is very difficult to even like the entire packet is encrypted, so you cannot get access to any of the payload, right? And uses different kinds of persistent techniques, like for example, original Mirai basically lost control after reboot. So since they are in the memory, right? Once you have a reboot, the file is lost. But the newer variants basically reinfect devices to maintain control, and they also leave minimal traces, right? For example, like fileless malware. And what is the attack execution? They launch large scale distributed denial of service attacks like TCP, SYN flood attacks, UDP floods, and disrupting target networks, and generates high abnormal network activity. So these are the key stages: recon, exploitation, command and control communication, persistence, and attack execution. So what is the key takeaway? Detecting Mirai is challenging due to stealthy recon and persistence techniques. Just a second, sorry. Yeah, so detecting Mirai is early is challenging. What do I mean by that is, it is happening in multiple stages: recon, exploitation, CNC, persistence, and attack execution. So these are different stages. If we can detect right in the early stages, right, and especially identify that this is Mirai, right, it requires very good intelligence analysis techniques for you to identify Mirai early, right? Because once multiple stages are completed, the impact already starts to show on the system or the network, or basically on the entire ecosystem, right? So that is why it is important to detect it early. That is the major key problem statement that we are trying to address, right? So real world examples of botnet attacks, for example, Mirai botnet devices affected over 600,000 devices, including CCTV cameras, routers, DVRs. What is the impact? Launched a massive distributed denial of service attack and on DIN DNS, disrupting major internet services. So it brought down platforms like Netflix, Twitter, Amazon, GitHub, and PayPal in the year 2016. So basically highlighted the risks of default IoT credentials leading to better security policies. Like that, we have several other real world examples like Mustik botnet. It exploited this vulnerability, CVE, Common Vulnerabilities Enumeration 2023, with this number, right? And it basically affected the cloud and containerized environments as well, right? So requiring new strategies for its defense. Defensive measures against botnets, we can have device level security, network level security, and cloud or ISP level security. Our means the major solution that can be applied to this is network based intrusion detection systems, where the large amount of packets that are generated, right, that we are receiving has to be analyzed to understand the underlying intelligence. If you can recollect, that's what we were talking about when we were talking about the NLP techniques. You have lot of information that is being received in the form of packet captures, right? You are capturing lot of these packet capture files, right? These files are these PCAP files are either can be correlated, and there might be a correlation between a packet that you have received at, let us say, some time instance, and a packet that has been received at a later stage, right? So these two packets, these have to be correlated to develop some kind of actionable intelligence. That is where these ML and NLP techniques come into picture. So this I am not going through. So how did we try to identify this nature of Mirai in the early stage? Means the basic goal is to, you have lot of information that you are getting from different sources. You have to combine this information to ensure that you will apply some kind of machine learning and NLP techniques on this large amount of data to generate actionable intelligence, right? For us, the actionable intelligence means whether we are able to detect means existence of Mirai in the early stage. Early stage means during the recon stage or during the exploitation stage. That's what is our aim, right? So how did we come about this problem is that we have first looked at what are the different botnet data sets that are available for us for research, right? So these are the different data sets that are available: IoT 23, MedB IoT, CIC IoT 23, NBA IoT, and TON IoT, right? I have discussed in these things in my first lecture as well, right? So there the topic was different. Here the context is different. Here I am trying to identify whether we can detect the existence of Mirai attack, right? When you have huge amounts of varied data from different sources, right? Since generating that level of data is a major challenge, so we try to first experiment with these data sets. So what we are trying to establish is that most botnet detection mechanisms rely on network traffic analysis. Detection models are often trained on known attack behaviors, making them vulnerable to evasion techniques, right? So these data sets do not have any kind of granular information of different stages of botnet cycle, right? And Mirai variants with modified source code can actually bypass traditional detection mechanisms. So that's how we have established this motivation. So what we are trying to do is investigate whether stage wise detection can happen to improve early threat identification, and also highlight what could be the limitations of network based detection and exploration techniques, right? So this is the first case study that I was talking about, whether we can do stage wise detection of Mirai, right? So the main objective is that detection of Mirai botnet at different life cycle stages to enhance early detection. What is the major problem here? The problem is that traditional detection mechanisms focus only on attack execution, missing early stage indicators. Means whatever is happening, like for example, there is a recon action that is happening, right? These data sets do not capture that, so these early stage threat indicators are not available for us, right? So what the approach that we could follow is that identify any kind of unique network behaviors in early life cycle stage, for example during recon or exploitation or command and control stage, right? What are those specific network behavior that I can look into and that I can generate as an actionable intelligence for my model? Once I have done that, the other major task is to develop stage-wise machine learning models for early stage Mirai detection, right? So what is its significance? Basically, when you have something like early detection, then we can prevent large scale IoT botnet attacks before they actually happen, right? This is a second case study that I am going to show you. Once you have done that, assess limitations of network log based detection when you can modify Mirai source code, right? So you have means you will use, now we are thinking like an attacker. Previously we are thinking like a defense, means we are trying to develop a defensive solution. Then we are also trying to break the existing system. What we are doing is that we are trying to see whether I can use some kind of automated techniques to change the source code of malware, right? And what impact it will have on my detection model, right? So understand the difference. First, I am developing a model to uh, understand or to validate its reliability. I am trying to modify the source code of malwares and trying to launch an attack and verifying whether the model is able to detect that particular action or not, right? So what is the problem here? Most detection models rely on Mirai's known network patterns, right? If the attacker can modify Mirai's source code, traditional models may fail, right? So that's why what is the key challenge here? The key challenge is that modified Mirai versions leave no traces in the standard network logs, right? Since we have modified earlier, what used to be acting as an indicators of compromise, now they are no longer acting as an indicators of compromise. So basically there are no traces left. So these traditional models will fail, right? So what is a proposed direction in which we can think of is explore different alternative techniques, right? For example, augment network records with some other type of records like system logs. So now what we are trying to do is that we are trying to apply explainable AI techniques for Mirai detection stage wise, right? So what basically have to be first established is that we have to have diverse set of information. One set of information might not be sufficient, because Mirai that is targeting an industrial network, or Mirai that is targeting medical devices or home devices, right? So they, I mean, unless you have some kind of cross-domain approach, you cannot say that the proposed system can work for different types of Mirai settings, right? So what the first step that we have done is we have tried to integrate these three varied data sets: IoT 23, CIC IoT 2023, and MedBee IoT, right? So these data sets, why they have chosen? Because they lack full cycle coverage. They have only mainly like those components that are reflecting the later parts of the Mirai, right? So what we have done is we integrate multiple data sets to provide complete life cycle representation, right? Then we used some kind of explainable AI techniques to enhance its interpretability and protect proactive security. This is where the AI techniques come into picture, right? So the major contribution is in terms of enriched Mirai dataset, that is basically integrated IoT 23, this and this dataset, right? And once you have that, then you have stage-wise classification framework, where we have applied different ML techniques and NLP techniques to do this classification. Then we have given a SHAP-based interpretability for transparent decision making, right? So if you can see that the results are not so encouraging, but good enough, because we are trying to do by integrating multiple different cross-domain data sets, right? So this 91% is much better than a 99.9% accurate model on a single data, right? So that's what is the major problem that we have solved, right? So how to do this? How we can do this, right? From the PCAP files of the multiple data sets, we can use tools like Zeek, right, to obtain the connection log files, right? The features related to Mirai can be extracted, and the data from these sources are mixed proportionately and standardized in a stage-wise mixture, right? So once you have developed these data into multiple stages like recon, exploitation, etc., right, you have to see that how these can be integrated and how it can help in understanding the Mirai's life cycle to improve the security measure. Right. Once you have that, a stage-wise detection system basically can ensure that timely mitigation before large-scale attacks can occur. Right. So if you see that in IoT 23 there are recon samples, but they are but in these two they are not. But in IoT 23 there are no exploitation but CNC samples and attack execution. But in this you have only attack execution. On this you have exploitation and communication. So once you combine these three, you get multiple stages information, right? So once you have these multiple stages information, then you have to then you can basically use these existing data sets to provide partial coverage of Mirai cycle missing key early stage behaviors, right? So what we have done is we bridged the gap by merging multiple data sets into a single comprehensive framework, right? The main aim is to enhance the interpretability and also develop proactive response capabilities, right? This I am skipping basically what others have done. Right. So the major observation that we can derive from this key related works is that most existing works focus on later attack stages like distributed denial of service, right? Distributed denial of service, what is a major indicator? Suddenly you see that there is an increase in number of packets that you are receiving, right? So once that stage is arrived, then there is very minimal action that can be taken, right? That can be suitable for developing a machine learning model, but that cannot be proposed as a solution for in the real world, right? So it has to happen early, right? So none of these works basically address the full life cycle detection from recon to attack detection, right? So what we are trying to do is that by using these ML techniques, how we are detecting Mirai at as early as possible. So this is a strategy that we have used. We have used benign samples from all these three data sets. For recon, we are using IoT 23 for horizontal port scans. For exploitation, we are using brute force attacks from CIC IoT. For CNC communication, we are using FD, heartbeat, and CNC traffic. From MedB IoT, we are using spread and command and control traffic. For attack execution, we are using DDoS samples, GREIP, and UDP samples, right? FD means file download, right? So command and control, you are using file download, heartbeat, and command and control traffic. So like for example, attack explanation or attack execution, basically generic routing, encapsulation IP and UDP, these are the most common vectors when you are having a large scale Mirai, right? So what are the various steps that we involved is first, as I said, data pre-processing, right? Cleaning the merged data set and resolving any kind of ambiguity that we have. Once that is done, then we carried out the model training, right? Model training basically involves training using random forest and XGBoost classifiers, right? Once that is done, we have evaluated for these typical evaluation parameters, right? The major outcome of this is a life cycle oriented detection system addressing stage-wise detection challenges in IoT environment. So these are the details of the data set. We had almost 500,000 total samples across 5 life cycles. Training has been split into 80-20%. Balanced data set to mitigate class imbalance issues, right? We have used these two techniques, RF and XGB, right? These are the evaluation metrics. So the overall accuracy that we derived across strategies, if we can see, attack is one, right? But benign, CNC, exploitation, the overall average is 0.92. So we have achieved an accuracy of 92% with strong performance in detecting attacks. And lower recall for CNC communication indicates potential misclassifications. So this is XGBoost. Overall is 0.91, but if you can see, CNC is the recall is 0.66, right? Which is slightly lower than random forest, right? So if we compare the performance of these two, random forest basically performs better overall, but both models struggles with CNC detection, suggesting the need for feature engineering or hybrid models. So basically, if we see that the command and control communication, the samples that we had, using which the recall is only 0.66, right? So we have to improve this, right? To improve this, basically we need to do some kind of feature engineering, or we have to build some kind of hybrid model. So this is the ROC curve that for random forest, right? The ROC curve basically shows that random forest achieves a high area under the curve, indicating strong classification performance, right? The model performs well across most classes, but has slight weaknesses in this in detecting command and control communications. So this is a performance for XGBoost, right? So if you see that, it is slightly lower compared to random forest, but it maintains high precision but struggles with recall and command and control detection, right? So what basically we are trying to conclude here from this analysis is that if we have to integrate data from multiple sources, especially when you have a network like IoT, right? You cannot use the same tools that you have been using till now. You have to have automated mechanisms to analyze these different correlated and sometimes unrelated data sources and ensure that intelligence is generated using these AI and NLP tools, right? That is a major conclusion. So, what basically led to this, right? That is done using this SHAP analysis, means whatever we have done, how to explain those results, right? For that, we have done some kind of SHAP analysis. SHAP stands for Shapely Additive Explanations, right? Basically, it's a game theoretic approach to explain whatever the ML model predictions, right? It assigns importance values to each feature, showing what feature contributes to the model decision making process, right? So for example, as I said, my model is giving me 92% accuracy, right? So how am I arriving at the decision? What aspects of my model is contributing to such a decision, right? So that needs to be known for transparency of the model and for also understanding the overall effect on the model, right? So that's why we use SHAP. And why we use SHAP here is that traditional ML models act as black boxes and SHAP improves interpretability. So and it helps identify which network traffic features contribute most to the Mirai detection. And it also enhances the trust in AI-driven security solutions, making the model more explainable for real-world use. So these are SHAP analysis for reconnaissance stage, right? So if you see after this analysis, we could figure out that the duration is the feature that is contributing most highly to the detection of the recon stage, followed by secure IP, source IP bytes, connection state, source packets, history, and connection state reset. These are the different features means in the decreasing order, right? So with duration being the highest or most significant feature. This for exploitation stage. For the exploitation stage, the major feature is local source. For command and communication stage, the major feature again is duration and the source IP bytes, very closely related. And for the attack stage, we have connection reset, right? That is a major contributing factor or major contributing feature for the detection. So for the also done for the benign stage, right? What are the major features that is basically forcing my model to classify as benign? So this is a summary of different features that contribute to the performance of the model: attack stage, benign stage, CNC communication, recon, etc. Right? So basically summarizing the entire analysis of SHAP. So what basically can we conclude once we have done this, right? we could understand that for you to generate intelligence, you have to integrate multiple data sources first. And majority of the works that are being done using network traffic cannot work when you have this wide diverse set of data and with like evolving malwares, right? So that's why we need to have more advanced techniques to detect these changing malwares, right? And we also need to have some kind of explainability to ensure that whatever the model is saying, like to build the trustworthiness of the model, right? So these are some future directions for this particular challenge of using ML and NLP techniques for detection of botnets, right? I will show you another interesting challenge here, right? Very quickly, right? We have around 10-15 minutes left. What are the major factors that are contributing or that are preventing the detection of malware like Mirai from only network logs, right? Means if I rely on only on network logs or network traffic, right? Why any model built on such a single source will fail, right? That is a major goal of my case study, right? What we are trying to show is Mirai basically has some limitation. If we are able to explore or if we are able to make some changes to the source code, Mirai source code, which is available, open source, right? Then what I can do is that I can ensure that behavioral analysis links like source code modifications can be done to network traffic, right? And then only few studies actually explore the TCP flag randomization and protocol switching, right? So what we are trying to do is that we are trying to map Mirai source code to network access and make suitable modifications, right? I will skip this part and mainly try to show you how we are doing this source code magnification. Basic methodology is that we analyze Mirai's lifecycle using network traffic data and source code correlation. What we are doing is that we are combining again these two data sets to include all lifecycle stages and feature validation using multiple techniques to ensure robustness, right? These are the different phases that we are trying to do: recon, exploitation, infection, persistence, propagation, and attack detection, right? The techniques that we are using for feature explainability is Pearson correlation, random forest feature importance, logistic regression weights, and SHAP analysis. All these techniques we are using for feature explainability and validation of the model, right? So we, as I've said, we have used these two data sets, IoT23 and CIC IoT23, right, to create an enriched data set of multiple stages of Mirai, right? This basically is a network log record of Mirai botnet. So basically the service is the protocol. Service is the protocol. Duration, source bytes, how many bytes have been received, destination bytes, connection state, right? Connection state S0, S3, SH, and SF, right? For example, origin packets, IP bytes, right? And service type, right? The key source modules are these: scanner.c, table.c, loader.c, attacker.c. These are the main files in the source code of malware, right? Like C, for example, the functions in Mirai source code that are responsible for scanning, means these are the functions that are responsible for scanning in the Mirai malware, right? So this is the original code. This is the original code where we are doing attack scan and rand next, generate random IP addresses for scanning next set of IP addresses. This is the original source code, right? We are modifying this. Right? We are modifying the source code, right? We are adding new ways in which you can scan IP addresses, right? The original source code basically generates TCP traffic with incomplete SYN handshakes, right? Leaving detectable traces in network logs, right? If you remember, TCP works in this way. You send a SYN packet, SYN-ACK packet, and you get an ACK packet, acknowledgement packet, synchronization packet, synchronization acknowledgement packet, and acknowledgement packet. This we call it as three-way TCP handshake, right? So what this earlier source code was doing is that it used to leave the TCP after SYN, right? SYN handshake is not completed, right? In the S0 connection state. So this can be easily detected in the network trace, right? What we have done is the modified basically source code introduces random delays and switches to UDP. So once we do that, we hide the activity of the attacker, right? As I have said, the first part is defensive technique. The second part is how we can actually break the model itself, right? So I am modifying the source code, right? This we are doing it, right? See, we are adding a random sleep, introduce random delay. For example, this is the original source code for exploitation phase, means exploit the attack. This is a modified source code, right? We are trying to give dynamic usernames, right? So we are modifying the source code to generate random usernames, right? The modified source code randomizes usernames and passwords, disrupting any kind of patterns that are typically associated with brute force attacks, right? So we are now trying to break the model, right? For example, infection phase, again, this is the original code. We are modifying it, right? We are modifying it by switching to different protocols. Instead of HTTP, we are switching to HTTPS, right? So basically, once you switch to HTTPS, the entire payload is encrypted, right? So any kind of activity that can be captured by the model is basically not happening, right? So once we have done this, then we have tried to analyze the feature specific analysis across different life cycle phases like this recon, exploitation, infection, and attack phase. So we have we have used these techniques, Pearson correlation. Basically, Pearson correlation actually measures the linear relationship between any two numerical values, right? So the reason why we used Pearson correlation here is that it identifies the key network features strongly associated with different Mirai botnet lifecycle stages. So it actually helps us to reduce the feature redundancy and improve model efficiency. So if you see the key features are TCP protocol, connection attempts, and high packet counts, right? The correlation factor is 0.99. With this correlation is 0.95, right? Like that, for different key features, the correlation constant is derived, right? So that basically shows that what features are strongly correlated to each other. Similarly, we have done for other stages as well, right? Recon, exploitation, infection, and attack. So recon has highest SHAP value for that is 0.6064, highlighting incomplete SYN handshakes. Similarly, for other types of other stages, we calculated the SHAP value. Like for example, local originator has the highest SHAP value of 0.184, confirming that this is the major factor when it comes to brute force login detection, right? So what is the impact of these source code modifications, right? The modifications to source code actually reveal how attackers can hide their activity in the network trace, right? Once you can actually hide your activity in the network trace, so even if you have a machine learning model or any kind of analytical model, it cannot detect the patterns that are hidden because of the modifications in the source code, right? So what what is the major key takeaway is that we need to have need for multimodal detection. That's what I said in the beginning of this particular talk, where we have to integrate system level telemetry, right? For example, log records, device logs, etc. All these sources are different formats. For example, pcap files, right? And log records, json files, pdf files, right? All these are different multimodal sources, and all these have to be integrated to build a more resilient and reliable model for malware detection. So uh, this basically is a conclusion of this particular case study, right? Uh, so what can be done further, right? What can be done further, right? We have to investigate if there are any advanced evasion techniques that can impact the life cycle detection accuracy. We have to emphasize on developing hybrid models that can combine system level logs, that's what I have been saying, with network traffic analysis, right? Implement some kind of real time anomaly detection frameworks in live IoT environment, conduct this training, right? And we can extend this research to other malware families to generalize the findings, right? These are the possible directions that one can take up, right? So these are the references that I have used for this making this presentation. So as this particular thing has been part of the research work that we are doing for Ministry of Electronics and Information Technology, Cybersecurity Division. This is an actively ongoing project that we are doing, where we are trying to analyze uh, different kinds of AI techniques like machine learning, federated learning, and other AI techniques to analyze cybersecurity threats, right? Thank you so much for patiently hearing. I know that it's 9 o'clock, and most of you have to go back to your job tomorrow morning. So I'm like, I understand. So I will take any quick questions if you have quickly, and then we can actually conclude. I can understand if you do not have any specific questions right now, because lot of information to process in such short time, right? Lot of seemingly correlated topics, but kind of need further understanding, right? So unless you are working in this direction and you are actively engaged in this direction, I understand that. So if you I will, once I share the slides, if you have anything to ask offline, you can please email me. My email ID is present in the slides, right? So let's wait for another 2 minutes if somebody has any question. Sir, are you here? Venkatramulu sir, are you here? Hello, sorry. I just called up Venkatramulu sir, and he's having some issue with the mic, right? So I guess he's trying to fix that. So just let us wait for a minute. So-
Hello?
Yes, sir. Vinbadin, sir.
Yeah, is it audible?
Yes. It is audible. It is audible.
Yeah, okay. Yeah. Thank you. Thank you, Rakesh sir, for your wonderful session. And really, I'm very happy to see you on both sessions. And you really given a good, valuable input to our dear participants. Yeah, do you have any queries? You can ask participants.
And
Yeah.
I think they might also be facing that unmuting problem.
Okay.
So otherwise, somebody who should be saying something.
Okay.
It will not be so because either yes or no, somebody will be saying thank you minimum.
Yeah.
So I think that's why they are also not responding. Maybe
Yeah.
comment. Maybe sir, we
Actually,
can actually enable comment box.
okay.
We can ask, can
Right.
somebody show some reaction saying that whether you are able to hear
Saying
us
that
and
raise the hand.
uh,
No one is
Yeah.
raising their hands.
Yeah,
The
no,
madam.
everybody is raising. Now they are raising. Yeah, I think
So
they are.
actually, some participants unmuting and in the background, there a lot of disturbance is coming. So
Yeah,
that is the reason everybody is muted.
So I guess that's the reason they are unable to talk.
Yeah.
No problem, sir. Means maybe
So
you can
tomorrow onwards, definitely
you
at the
can
end of the
fix
session, we will unmute all the participants.
participate.
Dear participants, sorry for this muted at the end. So due to some reasons, because a lot of disturbance is coming while speaking.
Yeah. I think they do understand that sometimes means crosstalk creates challenges when. All right, sir. Thank you so much, sir, for
Yeah,
patiently hearing. I think we cannot hold them back. I think whether they must also be waiting for their dinner, and they need to go back to their office
yeah.
tomorrow morning. So, without holding much back, if you have anything, please do reach out. You can also write to me over email if you have any specific things regarding these two topics that I have delivered on. Right, rest I think Venkatramulu sir is there for other speakers. Right, thank you so much, sir, for giving this opportunity.
Yeah,
I'll
thank you.
be
Thank you, Rakesh.
thank thanks, sir,
Yeah,
thanks. Bye.
good night.
Bye.
Good night.
Good night.
Yeah, dear participants, all of you, good night. Yeah, you can leave.